Are you able to see my screen?
Yes, sir.
Okay, fine. So this was the problem we discussed in the last class, and at the same time, by working out this problem, we understood how estimation of the peak drainage discharge is conducted and or calculated. Now, with this, the next part, which is very important, is hydraulic designs of sewers and stormwater drains, the stormwater drain sections. So, for doing that, we'll be discussing in today's class. And with regard to that, there are sewers and stormwater drains, and we need to design them as open channels, except when it is specially required to design them as flowing under pressure, but that is very very rare. And in case of specialist situation like inverted siphons or so, and discharge lines from sewage pumping stations which always flow under pressure, in all those cases you have flow under pressure. However, those are the very typical situations we don't want to consider in general. And so in general, usually, as I told, that we have to consider as open channel. So there are various empirical formulas which are available and have been suggested for determining the gradients necessary to obtain design velocities of flow in sewers or in drains, wherever is you can actually assume it as an open channel. You can apply this formula which we are going to discuss now. Among different proposed empirical formula, Chase's formula is the most adopted one and most popular one, I would say. In 1775, Chase developed this formula, and this formula says that the velocity of flow in the channel is equals to C into root RS, where C is the Chase's constant, remember, and it's basically a constant, and we have to see how we can determine the Chase's constant. Apart from that, rest of the two parameters R and S are associated with your open channel. So it's basically the characteristics of open channel. So R is the hydraulic mean radius of the channels or hydraulic mean depth of the channel. So that is basically A by P. A is the area of the channel and P is the weighted perimeter of the channel. If you can remember what you have studied in your fluid mechanics course, then it will be easier for you to understand, and you can connect very easily. So once you get R by determining A, which is the area of the channel, and P is the weighted perimeter of the channel. So here one situation has been taken as example. If you have a circular section running full, then that R would become D by 4. Likewise, for different sections and different flowing conditions, whether it is running full or running half or partially, one third. So accordingly, the value of small r gets changed. All of you, I guess, can remember that. So, uh, so accordingly, we'll get the relation, and then ACE is basically the hydraulic gradient. So that is equal to the ground slope for uniform flows, and that can also be, in other words, said that the head drop between the 2 points divided by the length. So this is known to all of you if you can remember what you have studied in your soil mechanics 1 while determining the hydraulic gradient in the permeability chapter. So the same thing here we are actually mentioning as S. So it is basically the head drop between 2 points. Uh, and when you discussed about the seepage and flow rates in that particular chapter also, I guess you determined the hydraulic gradient, and from there critical hydraulic gradient and so on. So we are not going in the details. For us, what is required is only the small s, and A, as I have already mentioned, C is the Chase's constant. Now this Chase's constant, it depends upon various factors. such as the size and the shape of the channel. That's pretty obvious that it basically depends upon the characteristics of the open channel and roughness of the channel surface. This is also very important to remember. The hydraulic characteristics of the channel and the value of C usually is obtained by using either Cooter's formula or by employing Bézins's formula, and we are going to see that by employing these two formula how we are going to get the value of small c, that is Chase's constant. So the channel section may, after that, once you get the value of capital V, so that is the velocity, the channel section can be designed Q equals to AV, where A is the flow area and of the cross section of the channel, and V is the flow velocity in the channel, which has been determined by the employing Chase's formula. Now, up till this, things are very clear to all of you, but now we need to concentrate on how to determine the value of small c. To do that, first we will consider Cooter's formula, and usually Cooter's formula is employed to determine the value of c. And how you can see over here, the formula is given c equals to you can see that we have a numerator and a denominator. You can go through the formula, and what are very important here is just to understand the different parameters associated with this formula. Now, apart from c, we have s, which is also the slope or gradient, hydraulic gradient, which actually we defined sometimes back. R is also known to you here, so these are the two terms I need not to discuss again. On the other hand, we have n, small n. You can see that. So small n is the rugosity coefficients, and then again this small n depends upon the type of the channel surface, and various values for different type of surface has been adopted, and these are provided in standard codal provisions, as well as in, if you follow any textbook, you'll get the value of rugosity coefficient depending upon different type of the channel surface. Now here I have actually given you the table where you can directly adopt the Manning's or Cooter's rugosity coefficient. So so since we are discussing here Cooter's, so same table can be adopted. So you can see that we have different material as a for the pipe. So salt glazed stone wares are there, cement concrete pipes are there, CI pipes are there, and then you have unglazed brick pipes wares, AC pipes are there, and then finally plastic pipes. Now, depending upon its smoothness, you can see there is a variation in the value of you know Cooter's rugosity coefficient, and you can take depending upon what type of pipe you are considering for your design. Now, this formula may be simplified by omitting the term 0.00155 by s, from the numerator as well as from the denominator, since this value will be very less. Once you consider the value of n, from this table, you will see that the influence of this particular term of 0.00155 by s is very less, which is negligible. So and the influence is like 0.001 in the overall value of n. That is why we don't sometimes we can simplify this formula, and you can use after omitting the term 0.00155 by s. Now the next one is Bézins's formula. As I mentioned, either we can employ Cooter's or we can employ Bézins's formula. So this is also another one formula to determine the C, that is Chase's constant. Now in Bézins's formula, you can see that again we have two different parameters, K and R, small r, and small r has been defined already a few times before, so I'm not going to talk about that. Now K is the Bézins's constant, and this K can be obtained from the table given over here, and then you can get the same table in some standard codal provisions. But any textbook would be convenient for you to find out these tables if you want to. I mean, though I am providing these tables in my slides, so you can just simply have an idea about it. You need not to remember these tables, because if in the exam question is asked, or numerical problems are given from this particular sections, so in most of the cases these values of mm, you see here capital K, or in previous case N, these values will be given, because it is difficult for student to remember the value of K or N. So again, it depends upon the surface. So nature of surface, so you can see that the way we discussed in case of footers, similarly we have here different considered different situation, or different types of surface for which the value has been given, and you can uh, go through these values, and you can take which one is most suitable for the design which you are performing. So with this, I'll move to the next slide. So that is Manning's formula. As we discussed, Chase's formula. The next one is Manning's formula. Manning's formula is very, very, popular in terms of adaptation. While mostly, in US and as well as in India, Manning's formula is widely used, and in designing the sewers and drains or stormwater sewers. So that is why Manning's formula you should really study, with a lot of concentration, because you can get problems associated with Manning's formula in the competitive exam as well. And it says this 1 by n into r to the power 2/3 into s to the power half. So this is what is Manning's formula. Here N and R and S have the same meaning which we discussed before, and the values of rugosity coefficient small n is similar to what we discussed in case of Cooter's rugosity coefficient. So that n and this n is in principle same, so you can use that particular table to determine the value of n. Rest of the two, like R and S, are known to you, and you have to be very, very smart in calculating the R value quickly, so that you can solve these problems efficiently within the limited time during the exam. Fine. So next one is Crimp and Burge formula. Crimp and Burge formula is also another one, simple formula usually used in UK, and in this case only the value of 1 by n in case of Manning's formula is altered. So in this case directly 83.5 is taken, 83.5 into r to the power 2/3 and into s to the power half. Now this formula is quite comparable with Manning's formula. As 1 by n equals to 83.5, which is taken, and in this case, in the value of n is 0.012. Now the n value is taken as fixed in this case, and this is identical for all different types of sphere materials, and so that is why logically Crimp and Burgess formula will not be that realistic which you can obtain through Manning's formula. Because you can do same calculation, you can take same problems, and you can obtain the value of V from both the formula, and you can check how much difference you are getting. Now for few case it will be fine, and Crimp and Burgess formula would also yield conservative results. However, for few cases or few types of material rather, there will be a difference in terms of the outcome, because in this case, regardless of what type of material or what type of surface, channel surface is it, you are basically taking the value of n as 0.012. Fine. Next, another one. So this is the fourth formula to determine the velocity by the help of empirical formula we are discussing. So this is the William Hazen's formula. You can see here. Now these formula is generally used for flows under pressure for designing water supply pipes, or sometimes it is used in case of sewers as well. Now you have to remember the uniqueness of William Hazen's formula. The uniqueness is nothing but it can be applied in case of flows under pressure. So in this case also, if you see, concentrate on the formula. So here, apart from R and S, we have another one term, that is CH. So CH is a coefficient, or we can say that coefficient of Williams-Hazan's formula, and that CH again can be obtained depending upon the type of material for the sphere pipes, and for different type of material, and we have different values. For new pipes is something, and for design purpose we can take a more conservative value, and we can do the design. Now we can see here we have concrete and RCC pipes, CI pipes, GI pipes, steel pipes, and steel pipes with different joints. So this is also very important. Depending upon the joint, the rugosity coefficient can be altered, and that has been incorporated in the formula of Hazan, Williams, and Hazans. So these are the different formula which are available, and what you should do is you should try to understand the difference between these formulas. And once you go through them with full concentration in exam also, if you cannot remember the exact formula, but this exercise would help you solve a problem, because during that time you will be able to remember, like if it is William Hazans, what parameters you need to change than what we discussed in case of chasing. So, or in case of Manning's. So mostly if you see Manning's, Crimp and Burgess, and Williams Hazans, these are quite identical in terms of form. So you can go through keeping all these things in your mind, so that you can easily remember the formula which is asked in the exam, and accordingly you can solve the problem, or you can do the design of that particular spheres or stormwater pipelines. Now with this, we'll move to the next part. So apart from the design of V and finally Q, that is the discharge, we actually have to have some conception or some theoretical aspect into our mind, and those are the things which I'm going to discuss now. So maximum velocity, minimum velocity, how much we can take, those things actually I'm going to discuss. So we'll move to the next slide and we'll discuss about those things. Now if you see here, these are the things we are going to talk about now here in this case. So when I say hydraulic design of spheres, so what are the general considerations which we need to keep in our mind? So you can see here that generally the spheres are laid at steeper gradients, falling towards the outfall point with circular pipe cross sections. Usually it is preferred to use circular pipe sections. However, you have to remember here, there might be one question which may come to your mind, and you should have asked to me, sir, all these pipes are actually underground pipes, but we are considering them as open channel flow. The reason being, in this case, gravity is the main influencer for this material to get conveyed from one point to another point. Another one thing is, these are not running full in most of the time, so there is no chance of getting under pressure, and it will just simply move from one point to another point while partially full, and that is the reason we consider them as open channel flow, and accordingly we apply different formula associated with open channel flow to design the velocity and subsequently the discharge. So this is very important to remember. Next is stormwater drains are separately constructed as surface drains at suitable gradient, either rectangular or trapezoidal. Now, so this is another one thing. When I talk about sphere, at the same time I talk about stormwater drainage. Now, these stormwater drains are actually, sometimes, in case of partially, or in case of separate, or in case of partially separate, or what we have is we have a separate provision for the stormwater. Those are stormwater drains. Now, what is done is stormwater drains are constructed separately at the ground surface itself. So by doing that, you can reduce the cost of construction to some extent if you are not doing these as underground, and it is not required also because that water is not contaminated as such, and it doesn't contain so many toxicity present into it. So that is the reason we keep it as as surface drains, and we need to provide suitable gradient. And in this case, since these are surfacial, we can design them as rectangular or trapezoidal section as well. Now, sewers are designed to carry the maximum quantity of sanitary sewage likely to be produced from the area contributing to the particular sewer. So we need to design this accordingly to the maximum quantity. Why? Because if the maximum predicted quantity comes, the sewerage system would be able to handle them without creating any problem in the future. So that is why we need to predict the population the way we did in previous cases. So while talking about water supply, so you basically first try to understand the population forecasting. Once you do that, you understand that how much will be the population after a certain periods of a certain number of decades. Accordingly, you can understand how much will be the overall water consumption, and consequently how much would be the overall sewage production, and accordingly you may have the maximum quantity of sanitary sewage which is going to come in a particular sewage. And keeping that in your mind, you can simply design. Now, next is stormwater drains are designed to carry the maximum storm runoff that is likely to be produced by the contributing catchment area from a rain of design frequency and of duration equal to the time of concentration. So that is why earlier we spent a lot of time in determining the time of concentration, critical rainfall, duration, those things, because ultimately you are going to measure the maximum storm runoff, and that is very important for designing the stormwater drains. So remember, these are the critical steps which needs to be followed to do a efficient design or connected design, which would be able to handle all sorts of maximum discharge in terms of stormwater as well as in terms of sewage. Fine. Next is the requirements of design and planning of sewerage system. So this is also very important. So following are the aspects which should be considered while designing the system. The first one is the sewers provided should be adequate in size to avoid overflow and possible health hazards. So you have to remember that sewers, what you are going to provide should be adequate. If there is a overflow, then a lot of issues is going to come, and finally that can be a health hazard. That can contaminate the soil, that can contaminate the water, often that can contaminate the air also. So all the different components of pure environment is going to be contaminated if you do not have proper sewerage systems. And that is why adequate size is a very important aspect, needs to be considered while designing and planning of sewerage system. Now, for evaluating proper diameter of sewer, correct estimation of sewage discharge is necessary. That is what actually I was talking about sometimes back. The flow velocity inside the sewer should neither be so large as to require heavy excavation and high lift pumping, nor should be so small causing deposition of the solid in the sewers. Now this thing you need to imagine sitting within the sewer lines itself, otherwise you will never understand. So now if you need high flow velocity, then you need some extra power to generate that high flow velocity, and that can be done only by the help of lifting pump. But running a pump with such a huge volume of sewage is always not economical, and it will make the entire system uneconomical, or so that will be difficult for the municipality or for the authority to run for a longer time period. And that is why we need to consider, at the same time the flow velocity should not be so high that it can create cover of the pipe material. So that is another one aspect. And while talking about the less velocity, if the sphere velocity is less than a certain value, then all the solid, these are basically liquid and sometimes semi-solid which is moving through the spheres. Now if it is less than that, all the solids will get deposited at the bottom, and they will not be able to move or roll down in the lower points, and thereby with respect to time you will end up reducing the diameter of the spheres. And we, as an engineer, don't want that to happen. That is not very desirable. What you need in that case is you have to lift up all the excavate, you have to lift up those pipes, and then you need to clean them, and again you have to install them. So this is a huge task uh, as far as money and cost of constructions are considered. And that is why all these aspects which I am discussing are very very important. Number four, the spheres should be laid at least 2 to 3 meter deep to carry sewage from basement. So this is a very important design aspect, or where you should construct the sewage. So it should be minimum at 2 to 3 meter depth to carry sewage from the basement. So you need to get that head which is required for the sewage to reach to the farthest point, and to do that we have to create the head difference from the basement, which is why 2 to 3 meter depth is provided. Now the sewage in spheres should follow under gravity. So that is the reason 0.5 to 0.8 full at design discharge, that is at the maximum estimated discharge, is considered. Now the sewage in sphere should always, it should convey to the point usually located in the low-lying area. So from where sewage is generated and where sewage is disposed of, so that there is a difference in the elevation in these 2 points. And at the same time, if you have a treatment plant, so the treatment plant is will also be located in some other place. So you have to plan accordingly, so that you can take the natural gradient available and take help of that to convey the sewage from one point to the another point wherever it is expected to be sent. And the final point says treatment plant should be designed taking into consideration the quality of raw sewage expected and to meet the discharge standard. So whenever we are discussing about sewage and treatment of sewage, so there are few aspects need to be considered. One is the quantity, another one is the concentration of different type of hazardous and toxic materials. And that is why we say quantity and quality both. Now if the quality is not that good, that means you need to put more effort to treat that particular sewage, and you have to bring them with all the potential contaminants present into it within the limits prescribed by the authority or by the government, or by the codal provision which are approved by the government. Once you can achieve that level of concentration, then only you are allowed to discharge those sewers, otherwise not. And so these are the requirements for design and planning of sewage system. So being an engineer, only just calculating the value of V and thereby the value of Q would not help. These points should be kept in your mind to design a holistically efficient sewage system. Now the important part which I am going to talk about is the freeboard. Now this is a components which are very very important, provision of freeboard in case of sewers and the stormwater drains. Now the sanitary sewers, as we have discussed before, are large enough to carry the maximum sewage discharge while flowing half or 3/4 or 2/3 full. Now, generally, these pipes of sizes, sewer pipes will have size less than 0.4 meter dia, and sometimes in most of the cases you will see a diameter of that range. Now, whatever extra we keep, that extra space therefore is left above the designed full supply line, will have an ample margin. as to act as a factor of safety to counteract against the few factors. Now, those factors are low estimates of the average and maximum flows. For a civil engineer, the term factor of safety is very important. Now, there are certain ways or tricks to adapt this factor of safety. Now, you can consider this freeboard as a form of factor of safety which is provided in case of sewers and in case of stormwater drains. Not only in case of sewers, but also in case of the different components of treatment plants associated with water supply and as well as wastewater is also um, given. So one is the low estimation of the average or maximum flows. Now, because of any wrong data gathering or some other illegal consumptions of some industry, sometimes the value which we predict is less. So, we provide the extra space if there is a variation up to a certain limit that can be accommodated by the hydraulic structures itself. Often, large-scale infiltration of stormwater due to wrong or illegal connections, and that of the underground water through cracks or open joints in the sewers, when you have such kind of issues, so the quantity of sewage which will be generated is also more, or the stormwater is also would be more. In that case, this freeboard is going to help. And if there is an unforeseen increase in the population, so what happens is, though we predict population because of some political or geographical happenings, you may observe a very drastic change in the population within a short period of time. Now, if that happens, then there is a huge difference in terms of production of sewage is concerned. Now, in that situation, the extra sewage which is getting produced can be taken care of by the help of the freeboard. Now, this freeboard, values of freeboard which actually has to be adopted, is given in this particular table. You can see, like the stormwater drains, as well as for the swirl system. Sometimes it is provided by here. In case of covered drains, the roof slabs will be laid at a level about the drains, highest level, and by the amount considering the freeboard. Fine. So that is in case of covered drains. But when you don't have cover, then directly you can provide that extra depth to accommodate this freeboard. Now you can see here, depending upon the overall discharge or rate of discharge, cubic meter per second, we can actually provide the freeboard, which is kept over here in the right hand side column. So from 0.3 meter to 1 meter, we have the range of the freeboard which is provided, and you can see them. Fine. The next important part which we are going to talk about is so before coming into this, let me tell you a few more things here. Now, the minimum of the 0.3 meter freeboard is generally provided for stormwater drains, right? And So now let us talk about the minimum velocity and the maximum velocity. So these are the very important aspect, which we need to consider. Now, the minimum velocity is also known as self-cleansing velocity. So what it does is, so the the velocity that would not permit the solids to settle down, which I was talking about sometimes back, and even scour the deposited particles of a given size is called as self-cleansing velocity. Now, there are two aspects here. One is it will not allow the solids to settle, and if there is a deposition which has happened already, will be scoured off if you are running that particular uh, in that particular velocity. So that is what is known as self-cleansing velocity and as well as the minimum velocity. Now the minimum velocity should at least develop once in a day so as not to allow any deposition in the source. So this is also very important. And if such deposition takes place, it will obstruct free flow, causing further deposition and finally leading to the complete blocking of the spheres. So this is very important to remember that at least once in a day you should achieve the minimum velocity just to ensure that there has not been any depositions accumulated within the spheres itself. Now this self-cleansing velocity and the expression for self-cleansing velocity was given by Silt. So this is known as Silt's expression, and as per Silt's expression, the if you see here, the self-cleansing velocity Vs is equals to, it's given over here. So the expression you can go through, and accordingly we can see different connotations which have been used. So we have K is the constant for clean inorganic solids, it is given, and as well as for organic solids it is given. So you can choose the value depending upon what type of solids that particular liquid is containing, and or the sewage is containing, and accordingly you can take the value of K. If dust which have been used, if dust is actually nothing but the Darcy's West friction factor. So for spheres it is taken as 0.03, and SS is the specific gravity of the sediments, which is also sometimes denoted as capital G. G is the acceleration due to gravity, and D dash is the diameter of the grain in meter. Now, this derivation of self-cleansing velocity is there in most of the textbook, so I am not going to derive it here. Now, you just try to find out and derive that, and keep it for your practice, because through that a lot of things will be much more clearer to you people, and at the same time you will be able to practice, because this is a very regular problem which may come in the semester exam. So that is why you all should practice this expression or derivation of Silt's expression for self-cleansing velocity. Fine. So with this, we'll stop today. We have maximum velocity that I'll discuss in the next class.